Thank you very much. And I'd like to thank the organisers for inviting me to give this talk. I'm going to tell you a little bit about the developments of bioimaging, specifically a technique known as electrical impedance tomography. I will take a few detours along the way to show you some of the history and the background and the developments that have spun off over the time period that I've been working on this. And this goes back frighteningly nearly 30 years of work to evolve this technology as we've gone through. I thought it was worth starting with a brief history of this development. It's taken a long time to gestate, but the spin-offs have been quite interesting and quite valuable as we've gone through. It's generated a lot of PhD projects, but it's also generated some fascinating side research. If we go back in history, and I'm looking primarily at the clinical developments. I seem to have lost the first part of my slide, but never mind. The more common term for this technology is known as electrical impedance tomography, but it was originally called applied impedance tomography. And one of the main pioneers in the early days was Brian Brown and David Barber of the Sheffield group. And they were the first group to produce pulmonary images, although there is some work that went back on the Webster camera that actually looked at it as well. Their work focused on a very simple concept of adapting CT tomography into the area of bioimaging. And it was very effective, but unfortunately, in some respects, the use of the simplicity of some of the algorithms they were held up the progress of this particular type of modality. There are still groups using this base system today, and clinical groups and clinicians are still doing valuable research work, even though the system is nearly 20 years old in the technology. It's used in a number of areas. It's used in breast, brain, gastric, emptying, lung, and we've been working on rectal cancer. It was first reported use over 100 years ago. So you see it's taken a little while for the biomedical community to adopt it. I don't have a picture of it, but there's a tractor where you put probes in the ground, and it's a geophysics measurement, and you measure the conductivity in the earth. And this was the very early days of geophysics. It's very successfully used in industrial work to look at concrete crack propagation. It looks at air bubbles, and the systems are designed specifically for one particular task. They're not generic systems, but they look at one particular problem and are designed very specific around that. There's even a group, or a couple of groups now, I should say, looking at developing EIT for measuring the quality of tree trunks and wood. One in Tennessee, and I know there's another one in Norway that's particularly interested in this area, where they're looking at whether the internals are rotting, the quality of wood, and in Canada, they're interested because they use the wooden poles as telegraph and cable carrying poles, and they want to know whether to cut them down and replace them or leave them alone, and they don't want to drill holes in. So it's quite successful in that area, and this is sort of the inception inside of that. I hope I'm not sort of boring anyone with explaining the basic principles, but I'd like to go through it with anyone who's not seen it before. The idea simply is that we look at the cellular property in the structure. So a cell has a membrane, which is a leaky capacitor, and the ionic currents, or the ions, will flow between the extracellular space at frequencies below roughly 70 kilohertz. They will stick to the track between the cells, and as you increase the frequency, then the current starts flowing into the cell membrane, and there are techniques to look at the nuclei up to 1 gigahertz. This is an example from brain. So the principle here is that when cells run out of energy, or in the case of stroke, the cells expand, and of course the space between the actual cells is restricted, so hence the impedance increases. So this is one mechanism that we can use to identify a physiological change. This is a cartoon of cancer. When cells become immortal, the cells start packing, and the cell density increases. So we're looking at a structure, this should be in 3D, but it's just to give you an idea. So the more cells there are, the more restrictions to the flow of ionic current, and therefore we get an impedance increase. When the cells are normal, the impedance is decreased. The range of frequencies can go from 20 hertz up to reportedly a megahertz. The megahertz is to look at dispersion so that we can normalize the dispersion. We can go as low as DC. DC is very interesting in the brain because we look at neuronal depolarization and effectively the action potentials. This is one of the holy grails, if I can term it, of one of my colleagues to try and create a system that you could see the actual action potentials in the brain. We don't have systems to do this at the moment. Even functional MRI is not looking at this particular mechanism. This is work that we've been doing recently, but to give you an idea of the particular cancers, we're still working with Brian Brown. They developed a cervix probe, and the cervix probe is designed to look at normal and the invasive cancer. As you can see, as the different stages progress, the cell density is packing, and because of the packing density of the cells, then we get a change in the impedance profile. And so the idea here is to identify whether there's a possibility of cancer lesions, and then obviously surgical intervention is required. We are looking at a particular area which I'll tell you a bit about, which is rectal colon cancer. This is the normal area of the tissue, and here we have a higher packing density of cancer or tumor cells at the periphery. This is a commercial device. I should have said, I hope you're not eating lunch soon, because this is work we've been doing in St George's Hospital in London. This device is a commercial device, and we were talking about at the very beginning how we can translate technology across. This is not an imaging device specifically. It's a small wand with a probe down here. This is a wireless device, and I've been taking this down to the pathology lab. This is rectal surgery that goes on. I was informed it's keyhole surgery, but I'm debate how they can call this keyhole surgery. There's a small polyp here, a normal tissue, and here this is the frequency range at the bottom, and this is the impedance, and we can see a clear distinguishability between the normal and the tumor mass. So we know the technique works, it's quite viable. What we need is this difference in contrast to produce images and image maps. The problem at the moment with this technique, of course, is that you have to probe the site specifically and you have to scan the whole area till you find the tumor mass. So you have to have a knowledge of what you're looking for. It's not a technique where you can just map the whole surface and find the tumor map as yet. Tissue properties are well known. This is work from Gabriel. In the early 60s to 70s, bioimpedance was quite in fashion. Then optical tomography and optical imaging sort of came, raised its head above the parapet, and it's a very popular area. But of course, there's the depth of penetration that's an issue with the optical side and scattering in inverse. And so now the bioimpedance side is coming back. In the brain, we can see that the distinguishability between blood, bone, grey matter, white matter, and muscle. Again, these parameters show that there are clear distinguishable tissues that could be imaged, and on Rank's work going back to 64, which is cerebral cortex and spreading depression. Spreading depression is really an animal model, but they believe it's similar to migraine. I thought I'd give you just a very brief overview of the basic principles, and I'll touch on some of the mathematical aspects. The basic principle, and there's many variations on this, but if you imagine there's a region, and we started with the assumption in the early days that this was 2D, although IO is in 3D, so this is not a correct assumption. And we tend to take a lot of assumptions in this area. One of the problems with this area is the physics and mathematics are very complex and not well controlled. So we have to do a lot more work, but the technology is very cheap. If you take an MRI, the technology is very expensive, but the physics is well known and conditioned. You take a CT. What we do have is advantages, which we'll tell you about in a moment. This is 50 kilohertz. Again, the caveat is that we can put in different frequencies. This is a domain that has a particular conductivity, and we measure a voltage at a pair of electrodes. We actually measure all the way around. But if you keep the current constant and you change the conductivity or resistance of some region due to a physiological change, some description, you get a voltage change, and it's simply Ohm's law. So that's the crudest way of doing it. Of course, you then make multiple measurements around here, move the current source into a different position, and you build up a set of data that you can then translate into an image. What are the advantages and disadvantages? Well, it's low cost, order of magnitude about $10,000. It could even be cheaper if it was made on a large scale. So we're talking about very low cost technology. The subject can move while we're making the measurements. So we don't need the subject stationary to make the images, which is a great advantage. It has high temporal resolution. You can get up to 50 images a second, so you can look at heart rate variability, which is quite exciting. It produces 3D images, although the bugbear of most of the work that was done back in, I would say, the 80s was everyone was doing it 2D because they found that it wasn't tractable on the appropriate computing engines that they had available, so they reduced the dimension of property. It does not use any ionizing radiation, and as far as we know, there are no harmful side effects for applying small currents. Up to about 5 milliamps is the safe limit, RMS. It has good localization. Its downfall is its spatial resolution. It hasn't got as high a spatial resolution as the MRIs and the CTs of this world. But it also doesn't produce structural images. It produces images of physiological change and function. So what we're trying to do with this technology is not try and compete with the technologies that already exist. They do a good job. Use it in a place where there's a particular question that we need to answer which can't be done with the other technologies that are available. I'll concentrate on the history again. And the history really, most consistent one was the Sheffield system. Everyone around the world and the groups I know have built their own EIT system. Maybe good and bad reasons for that, because we tend to reinvent the wheel and go back again rather than extend it. There are companies like Draeger, Varsys or CareFusion were building it. I believe there's a company in Brazil now starting to build it, and even GE and other companies are getting involved. This shows you the development. They built the first Mark I, 16 channels, adjacent drive, and I'll tell you a bit more about that later, at 50 kilohertz. It was primarily all analog in its design. They then were commissioned to build a device to go on what was then the space program for Europe, so that in weightlessness, they could measure their lung function and pulmonary function. This is one of the big advantages it carried. This again was 50 kilohertz. It's portable, really. Moved along to digital in about 1990, then back into analog, because the digital, although it was okay, didn't quite cut it in terms of the performance, but they were increasing the band. And finally, the 3.5, which was 8 channels, so they reduced the number of channels, but they were looking at the different frequencies and up to digital. And in fact, the probe I showed you earlier has 1 channel of this device built into it. So the development has taken quite a while to get through inception. This was a picture I borrowed from Brian Brown's. You can see the original system, and you actually can go around to clinical groups still in the world, and you see these same boxes that are still there. A set of cables, the electrodes are stuck on manually to the person, and you can see on the old PC here an image of the respiratory function going on. Just to show you, let me just get this to function. These show the sliced images. Oh. Back again. These show the sliced images through the planes. The images are artificial in the sense that they are rasterized through the region where the electroplanes are, but the data exists outside of those planes because the whole model is there. So we present it in that form, and you can see some of the imaging there. I think this shows it up a little better if this will function. This shows the lung imaging, the volumetric change. So we can see that there are changes. This was done with the early back projection algorithm. And again, the back projection algorithm gave great limitations. The shape of the torso was assumed to be a cylinder, again, another flaw in the actual work that was done in the early stage, but it demonstrated functionally that it could work. What I don't have is actually to show you the speed, but there is an online video of fish swimming around a tank, and you can actually image the fish as they travel around the tank in real time, which is quite interesting. Incidentally, EIT and the imaging didn't come primarily from invention. There is a fish that uses the same bioimpedance imaging principle in nature, the zebrafish, to actually localize its prey. So we didn't invent this. We simply borrowed from nature what was already there. These are systems that have been evolving. Just to give you an idea, it gives you a perspective of the technology. Now, this is the VARSYS system. There's a little set of electronics there, a laptop on top, and a long cable of about 1.5 meters that goes to the child, which is really one of the problems with the systems that were being developed. This large amount of cable was driven screen, and of course there was a lot of parasitics of capacitance which reduced the performance. We developed this system in the early days. You'll see it later on an example. This is the head box, which has 64 electrodes. The base box, which we put the color lights on. No disrespect to clinicians, but they complained that if there's no lights flashing, they couldn't see whether it was working, so we stuck some lights on to show the channels, and an old-fashioned PC. We progressed this on because we started to realize we needed to bring the hardware up closer to the measurement source. So this is the 3.5 box, but the multiplexer for the system is based on the head, and this was a prototype with the electrodes going into the multiplexer and then the signals being transferred down to this box. The whole idea here is that if the patient is having an epileptic seizure, they can move, keep the technology on board, and then transmit the data. And in principle, we could use wireless connections as well, which is fairly straightforward. It's just the investment in there. Variations. EIT has not stood still over the time period, and we have these curious variations. This one is basically the same principle, but this is a breast image system. I'll show a bit more detail when I talk about the application. The subject lies prone with the breast hanging down, and there's hydraulic electrodes that are pushed in. This was done under Dartmouth, a large sponsored grant to work on this, to look actually from a military application, but it's to do with their medical insurance. We've also found groups combining. Now, electrodes are always a pain. When you put electrode on it, you have the electrode interface. You prefer not to. So one group in GART started to look at coils. Now, coils have less sensitivity, but they do have the advantage that you don't need contact. But of course, again, there's the question, can the subject move? Here is Korean physician, Professor Eun Jae Woo. We did some work back in, I think it was about 1990, and we started looking at the same system, and Eun Jae's taken it to the extreme. This is an MR EIT system. You may ask the question, why would you want to combine MR and EIT together? You get the negative parts of both, a large, expensive system. But what we've been trying to do is extrapolate the conductivity of living tissue, and then we can use it as a prior in the reconstruction algorithm. The downside of this technology is that you have to inject quite a large DC current. We worked about 100 microamps. You've got to get it down to 1. They've got it down to 16, reportedly about 10. They have got a PhD student to volunteer to stick his leg in it, but he's still, his muscles are seizing at the moment he does it. So I think he was desperate to get his PhD for doing this. But their claim to fame at the moment is that they can image Korean sausages, which may be a good use. I think they will get there in the end, but it's going to take a lot of work to actually develop it. So it's more of a research, not a practical clinical thing. And people have said to us before, very nice piece of research, but what's it going to be used clinically for? There is a system called T-Scan. It is being used commercially. It's sort of an impedance system. There's a little cheat goes on with T-Scan. They put more than the allowable current into the breast. They go up to about 10 milliamps. They get it under therapy rules under the FDA. And it is beginning to be used as a conjunct technology against other technologies for mammography. A little bit of words for the reconstruction. I won't go through this too much, but just show you two examples of one of the or two of the key problems. To solve the reconstruction problem, we need to solve the inverse problem. And the inverse is we're given the voltage and the current, and we need to find the conductivity. However, to do that, we need to solve the forward problem. So we have this equation, which we should be using the full Maxwell's, but that's complicated. There are a few reported papers on full Maxwell's. So we reduce it to Poisson's. We assume there's no sources in the domain, which we can get away with. And effectively, we're given the J and the conductivity, and we need to find the potential. And then we can find it by a number of different methods. We use FEM, BEM, or analytical methods. Analytical methods would be ideal, but the human body doesn't come in nice spheres and cylinders, so we need to actually adapt for that shape. The problem, of course, is it's nonlinear, ill-posed problem, and therefore, to make it tractable, we've often gone through the route of linearizing and regularizing and reducing the size of the problem, which works, but loses the information, and so we lose the quality. Most of the work, this is simplified again, is based on Grzelczyk's lead theory. So a voltage change is equal to this thing called Jacobian or sensitivity matrix times the vector of the conductivity. And of course, we get the inverse of that multiplied by the voltage gives us the conductivity. And we choose in here to construct the sensitivity matrix by assuming a basis function, either a pixel or a voxel or a tetrahedral element. And we reverse the current and the voltage to give us this function, which we form this sensitivity matrix. The advantage of some techniques in the linearized technique is we can compute this thing offline and just perform a simple vector matrix multiplication, so we can have the algorithms running very quickly. So to summarize the process, we make the measurements, we generate a mesh specifically of the particular clinical application, solve the forward problem, solve the inverse, rasterize it because it may not be in the same basis, and then we have to give it to a clinician and say, what does it mean? And it may not mean structure, it may mean change. For example, the images I showed you earlier were volumetric change. That color meant the total volume of the lung that was being changed in time, not necessarily the shape of the lung, which of course is what the respiratory clinicians need to know. They need to know how the lungs are expanding. And of course, as it's in 3D, particular applications like that are quite important because we still don't have a method in real time of looking at all the lung inflations. So the left lung might be working to compensate the right lung, the bottom of the lung might be working harder, and so we need to see that information. So here's a niche area which we can look at. Forward solvers, these are the most common ones, just to go through briefly. So preconditioner is incomplete Tarski or algebraic multigrid, and complete complex is incomplete LU. The solver precondition conjugate gradient, and we have a range of biconjugate gradients or general minimal residual as the way of solving it. So those are the forward solvers. The inverse, we have a choice. Most common is Tikhonov, but we use truncated SVD because you can tune it. You can adjust for the noise, which was quite handy. They're all offline solutions in the sense that they're very fast, and they do produce reasonable images. This particular one is a paper being published, I think 2 years ago, where we were having coffee and three of us sat down and said, there's so many different algorithms, how do we compare everything? We will produce something that is the gold standard to compare against things. And we ended up with a paper with about 25 people on it, and we now use that as the comparison. The nonlinear produces better images, but you need a very good PC and go away for about 5 days while it's trying to compute the inverse. That's the sort of order of magnitude. So we've got Gauss-Newton, we've got Lyrenberg-Markovich, and we've got variometric, and we've also got conjugate gradient. Now, when I give this talk to clinicians, I normally find that the sleep rate increases during this part of the talk. So one of my the students we had in the group decided to provide the happy face scenario. Not really objective, but it gives you a good idea. So robustness is where it falls over because the type of data we're dealing with. Convergence is where it iterates to a solution which is not applicable to SVD. Computation is how many days have you got to wait for the images. And image quality is partly a perception as well on that front. And we found that This one on the computation, but of course not the best image. And down here, the conjugate gradient was about the best that we had available at the time. This was back in 2004, and it is progressing over time. So I'll get this done. Right. New methods. We're starting to look at new approaches. This is Kalman and particle filter approach because we're beginning to actually find better mathematical techniques. So this is just an example. We're also introducing a new approach based on Fisher information because we can integrate the statistical parameters, Bayesian statistics within that approach. This is a group that is in Sweden and has expertise on this. And we find that we need to actually start being more adventurous in these algorithms. This is an example of inclusion with Fisher. This is a tank with water in, which is a common test structure that's used. This particular one was the quasi-Newton optimized with the Fisher information, and you can see the image's distinguishability is beginning to improve. One thing we don't do, unlike fMRI, we don't threshold. If I threshold these images, I can make them look wonderful. So we show them warts and all, all the artifacts, all the rubbish, because at this particular point, we're trying to optimize and improve the quality and the distinguishability. The injection protocols, we have a range of injection protocols. Applications dictate the type of injection we put in. If it's brain, we want to get more current into the central region. If it's lung, we're quite happy to deal with just more of the peripheral region in it. And early work on this, which I did back in 1996, the issue here is that you want to get as much information. So as much information would be a cosine. This is multiple patterns to improve the sensitivity. However, the hardware gets more complex. In the early days of the Rensselaer system, before you started using it, you had a technician sit there for an hour trimming all the pots to get them balanced exactly right before you could actually drive the system. So it's not going to be a very practical system in a clinical ward. So most people adopted the adjacent protocol. It doesn't have the same sensitivity to changes, but actually was a sort of compromise. We adopted the dynamic because we wanted to get more current in the central region. This is something I did when I was doing a PhD. What PhD students don't realize is their supervisors don't always tell them the truth. They don't tell them that it's impossible to image inside the brain, which I was told, or wasn't told, sorry. And of course, I naively went away and found a way of imaging inside the brain. So it's quite useful not to tell your students the entire truth, that everyone has tried in the field and failed, and then suddenly maybe there is another solution out there. They might curse you afterwards if it doesn't actually work, but on occasions you do actually get there. So the idea here was very simple and naive. If we couldn't get the current through by having the electrodes adjacent, then why don't we put them opposite? And then we wouldn't get as much information of independent information measurement, but as this was a low resolution technique in a sense, we would get more current going into the center. And we tried it with some phantoms. We made a stable phantom with plaster Paris ring, and this is the old Lagrange multiplier back projection algorithm, which I created. And we were able to see and distinguish with this barrier in the way, where most of the current is generally shunted around the outside of the periphery of the head. The other thing that we've now come on to is said that we've got so many variations, electrode shape, current protocols, parameters, noise, etc., etc. We don't really have a metric to decide the best. Everything is modeled on CT. You put a ring of electrodes around like a CT and you measure in a plane. And of course, this doesn't go in a plane. Are we using the best thing? In the head, when you moved from 2D to 3D, what was the optimum placement? So one of my postdocs has been working on looking at the Kramer-Bound concept and incorporating Fisher information. And the idea here is to try and find ways of actually measuring the optimum placement. So here's the electrodes going around. Here's a model of the left and right lung and the heart. And the convergence we can see as we move round, the right lung starts the best and converges quicker. The left lung catches up, and the heart never quite catches up because it's further away in terms of the information. This is a crude model at the moment, but we're taking this further forward because we want to know where do we stick the electrode, where do we inject to get the maximum information to get the best image, which is really been done on intuition, not on mathematical sound basis. I'm going to take you through some examples now, and these examples are projects we've been working on. We've been working on looking at neonate lung function. Now, this is a particular application area where there isn't another modality to actually use. What we don't have is enough data on the development and gestation of neonates because you want them unsedated, you want it non-assisted. Try asking a 5-year-old child or even a 4-year-old child to blow into a peak flow meter and to try and get information about their volumetric changes on their lungs. So non-compliance is quite important. We want them to wriggle and move, which is another thing. You can't say, go into the CT scanner, hold your breath, keep still, and we'll get a good picture. And we want it dynamic. What we did is we approached this rather than just looking at just one part of it, which many groups have done. We looked at the reconstruction, the image analysis, the hardware development using full custom silicon design, and the clinical evaluation. This was the Varsys system. As you can see, it had a cabling on here. These are the electrodes placed on the baby, which do take time to put on. And this was the sort of reconstruction you got when you played around with just the pure back projection. And I won't knock it because it actually was being used and still is being used to take clinical information, but it's limited in that sense. What we wanted to do was look at a number of challenges. I'm not going to show everything here, but I'll give you some idea. The contact placement, positions, the electrode. Normally in adults, we abrade the skin. You try doing that on a neonate and you have their parents lynching you while you're trying to just abrade the skin to get a good contact on them. So we can't abrade the skin. We have to use specific electrodes. We need, in the reconstruction procedure, as you'll see on the theme, one of the problems is that we need to know the boundary form. The conditioning of the forward problem is dependent on the boundary form, and we need that information. So we need to help EIT with some priors. If we don't put the boundary form in, we get artifacts where the mathematics tries to fit a solution to that known information. This was an EIT. What we're trying to aim for is a single device that will fit onto a single silicon chip that we can integrate into wearable technology to make the measurements. So the idea here is that instead of having that great box sitting, we will have a wearable technology that measures the whole boundary form, which we're progressing towards, and a wireless, hopefully, link to a base station to transmit the data. So the patient can move, jump up and down, do whatever they like, and all the information is transmitted offline. But we need this technology to be integrated in this form so that we can, one, get it on the patient, and two, get rid of that cabling, which introduces all the errors, the movement artifacts, and things like that. This is part of our wearable technology development, where we're using bend and stretch sensors. And one of my PhD students has looked at the optimum number of bend/stretch sensors to get the boundary formation in 3D, which we then feed back into the reconstruction algorithm to make a better image. And to show you how this works, we published this, but what we did, we said, right, do we need all the information to get the best image? So we said, let's start with a cylinder. Excluded cylinder is obviously an easy one, and if we can get away with that, we can even use an analytical solution. Obviously, the simplest approximation is elliptic form. That sort of models the torso in some respects. And here is where we take the correct boundary form shape, but we just extrude it down. And these are FEM meshes that we use, and there's 20K elements in there. This was showing where we're starting to move into 3D as well. We did have some information. You can CT abnormal babies, and this has an abnormality you can see raised here, erythrocephalus. But we use the boundary shape to actually extrapolate in our modeling, and we use some solid modeling to take that out. So this was our sort of crude model. This is not exactly patient-specific, because we know if we get patient-specific, we'll get it even better. But this gave us a good starting point in our model. So we tried the cylinder. This is the white cross is the trace. This is for about 5 seconds. These are the profiles of the white cross. This is full width half max, which we often use, which is sort of a little crude thresholding just to look at one particular region. And we can see sort of blobs with the image where the lungs are. This is taken, by the way, from real data, not modeled data. And we do know that there is a slight variation in the lungs because of the way the patient was lying. But we were interested to use real data than model data. We have checked it on model data. And you could get away with it, but it's not ideal. We then said, right, let's look at ellipse. And to our surprise, we started getting lots more artifacts occurring in here, and it really wasn't working very well. We then moved on to this extruded form, and our horror, it got worse rather than better. And finally, the conclusion was very simple. We needed the real form. And this actually, although it had a much better formation of the volumetric change, the heart, and also on this side, although it's reduced, there's consensus opinion that this particular subject did have less volumetric inflation on one lung to the other lung. And I'm only showing you part of the slice because even though the electrode ring is there, I can go down and look at the whole volume in there, which is in the paper. Brain. I spent many years working on the brain, and the brain was quite an interesting challenge because although the sort of area was quite limited in what we would use it for, it was this holy grail to look at neuronal depolarization, which my colleague is still working on. But what we wanted to do is to look at epilepsy. So the mechanisms that you can have is cell swelling, blood volume, temperature. Stroke is about 100%, spreading depression about 40%, epilepsy is 15%, and evoked potentials, which is, you wouldn't use this to look at evoked potentials, but we use it as a model, as a control. Now, this is slow in terms of tens of seconds, so you could get a similar to PET, maybe fMRI, but practical advantages, a heck of a lot cheaper. And the fast one, which is where we were looking for the action potentials, which is, my colleague had this idea that we would all rush out to the hardware shop and buy a system that we could stick on the TV and watch our brain activity as it worked. I wasn't entirely convinced that we would ever sell enough of these systems, but we don't have a tool to do this, and for psychology and other areas, this would be quite a radical tool. So we did the reconstruction. I just say text files, electrode combinations, we select geometry. In this case, we used a standard sensitivity matrix, inverted it using SVD, and reconstructed the image. When we did this, first of all, again, we used spheres, which is often used in inverse dipole modeling. It's used in other areas to see whether anything was there, and we came to the conclusion that we could see it in the sphere model. There was definitely, with the visual stimulus, which we used as the model, that there was activity. It wasn't great image artifacts, but then it decayed down. So excited, but still more work. We then went back to the drawing board and said, can we get rid of, use a sphere, an analytical solution that is shelled model using Granger multipliers, and then using an FVM model of a sphere, and again, also using this model, which is spheres. But we really want to use the proper head. The problem with the proper head is to build sophisticated FEM models is quite time-consuming. My colleague who works on them spends a week crafting them to get them to the perfection and all the integral details. It's not an automatic process at the moment, and so what we wanted to do was to try and find ways around this. So the question is, what happens when you put the right solution? So we took T1 and T2 weighted images, segmented them. This is just part of the process. This is the lofted rational B-spline to build the model. This is the models that we've got. You'll see a DBS electrode stuck in here because we have had a spin-off in this area to do this. I'll mention a little bit about that. These are the different compartments. Again, we would like to put left and right ventricles and everything else in, but again, computationally, it goes up. And these were the models that we were dealing with, showing you an example of the mesh and the number of nodes. It takes quite a bit of time to actually compute this, the full model. We have literature of measurements that have been made of the conductivity. We have a project now that we've helped some ethics over in King's in London, where we can actually take tissue samples live, after the operation and make better measurements, because some of these measurements were made with frozen tissue, but it allowed us to have parameters that we could use in our model. And we wanted to make sure that the models work. Now, there's a difficulty in here. Physiologically, the cell structure, if you try and take dead tissue, the cell structure is breaking down, so you don't get the right model. But there isn't a model. I have to rush on a bit. There isn't a model that actually is stable. So we used a unglazed skull. We went through different vegetable matter to see if we could find something stable and came across marrow or zucchini. And we built a marrow head. Our poor postdoc that had to do this and present this wasn't over keen on it, but it gave us a stable point to find out, can we see anything in this using this approach? We also persuaded someone to let us use an MRI scanner to see whether the internal structure was correct as well. And we tried this out and we said, right, has the image quality improved? Well, this is the Perspex rod, this is the sensitivity matrix using a sphere, and this is the reconstruction with the correct sensitivity matrix, not specifically on the head, but better shape, and we started to see localization. Well, the proof was, does it really work? So here we have a little head box. This is the electrodes onto the subject. These are 2 events of epileptic seizure that have occurred. During this seizure, we were able to image this in real time. So this was quite exciting. This is on the ward in telemetry that's 24 hours. So we were able to do this. So it demonstrated that we could do this. I'll just show a little bit of this video. Takes a little time, but I'd like to show just a short part. It's not seeming to run at the moment, so speed it up a little bit. Seems to be taking a bit longer to run, but I'll just show you various stages. There's the seizure coming on. You can see some artifacts in there, but that was due to the fact that we weren't quite had the correct model, but you begin to see that the seizure is identified. This is, by the way, why the subject is fitting. So there's movement in here at the same time. We've taken this slightly, this is a detour I was talking about. I've seen a talk earlier on in the conference about deep brain stimulation. These same head models that we're also applying to deep brain stimulation. So the spin-off of this is to use it for other technologies like DBS, which is used for Parkinson's essential tremor, etc. And we were able to use that same model to show the field potential inside the brain when the activation field goes through. And our plan is to use that information to improve the quality of the image reconstruction to show the activation field. This shows another slide of just dynamic imaging. Breast imaging, this is a project we're doing in collaboration with Dartmouth. So again, I showed you the beginnings of this. Patient lies prone, electrodes come out, hydraulically driven, I think they are at the moment. This is the model that they were using. Instead of actually recreating these models, we found a process where we morph the mesh to fit the registration points and then do the solution. So my colleague here was taking these sort of models, which are definitely nowhere near like the shape of what the breast should be, and actually get it closer to the real solution. Given the time, I'll just move on and show some of the examples. The breast here is hanging down a bit, but this is the same set of data, and this is with the non-ideal solution, and this is with the model closer to the fit. But it does demonstrate that we can use this technology for identifying tumor masses in breasts. Finally, the project we're working on at the moment is looking at colorectal cancer. And this is actually I think the third most common type of cancer in men, and this is the world, and the second most common type in women. It affects people over the age of 40, but of course, I won't be too long. The problem at the moment is we don't have a screening method that's non-invasive and regular. Patients turn up, they have blood in the stool, and they already have the condition, and so it's radical surgery that's going on, rather than going for a regular screening program. So it's not very glamorous, but it's very important. So what we've been doing is building models, and along with that probe, this is a model of the inclusion of the tumor mass, and these are the reconstructions. And the idea is to build an array of a device that will go up the rectal area and be able to scan like that probe to give us an image map across the whole of the technology. And just one final little bit. One of the problems with EIT is we talked about resolution, but now on the horizon are these things called nanoparticles. And nanoparticles are contrast agents. So what we've been doing is looking at the possibility of taking these nanoparticles and actually using them as a contrast agent. You can attach different ligands to them and change their conductivity properties. So this is some early work. It shows the different gold nanoparticles, and you can have iron with different increases and decreases associated with that. So our work at the moment is concentrating on combining this. We can deliver cytotoxic drugs, hopefully, and we can actually do ablation by heating the particles. This is a long-term project, so I've only just touched on this a little bit. So in summary, what we're saying is that this technology is evolving and growing. Like most technologies, we hope it will be there instantly, but it's going to take time to develop. I say time, it's taken 100 years in the geophysics. We're about 40 years into it on the medical, so we've got a few years to go. It's low cost. It's high temporal resolution, 3D, non-ionizing radiation, and we're putting it into areas where you can't use the other modalities. So it's not to compete in there, it's to solve problems that we can't already solve with the existing technologies. I'd like to thank a few people on here because obviously this is not only my work, but it's the work of quite a large group, and this is only just a fraction of the people there. Thank you very much.